Okay. So, since this is a talk, this is a chat. My name is Viktor. Nice to meet you.
Hi.
All right. So, a little bit of a background. I'm a software engineer at Utility Warehouse, where I develop event-driven microservices in Go. My formal education background is I have a bachelor's in computer science from University of Southampton and a background in competitive programming. If you wanted to reach out, and I think you should, if you have something to say, this QR code leads to my personal website. You can find my email, CV, GitHub link, and also on the second page, there's like a keyboard icon down in the corner. It's like a terminal emulator that I built. It's totally cool. You should check it out. All right, now to the talk itself, right? So there are a lot of optimization techniques that concern themselves with code reusability, efficiency, and stuff like this, right? But from time to time, you see a function that you don't expect any part of it to be reused in the future, and it seems like what it's doing is fairly efficient from the big O perspective, right? And yet you look at it and it's still like a wall of code and you're like, what the heck is all of this? This is too long, right? So then you go to to the person that wrote this function, maybe it's a PR review or something, and you say, your function is too long. And they say, well, I don't think so. I wrote it, I get it, right? So how long is too long, right? Okay, let's do a bit of audience engagement. How many of you think that 1,000 lines of code is too long for a function? Raise your hands. All right, that's pretty much everyone. Okay, no, keep your hands up. Okay, who thinks 500 is too long? Okay, what about 100? Okay, some people put their hands down. What about 50? So, okay, all right. So maybe, see, it's very subjective. Now, the whole deal with my talk is that I want to introduce a way of thinking about functional complexity, about the function itself, that is quantifiable and measurable, and allows you to derive heuristics for writing better, cleaner code, even though from the efficiency perspective, it doesn't change anything, right? So that we have better, readable code that is easy to maintain and read for the future generations to come. Now let's look at a few abstractions. There's two of them that I chose that would not work for that. So standard discrete math, domain, codomain, hides everything within the magic error. No one knows what's behind it, cannot access any information about the complexity of this function. Now, the functional complexity, the algorithmic complexity, what they teach in uni, the big O notation, you have to know every subroutine and how it works, and you have to assess their complexity first, and then you know the complexity of F. This is very deep down the tree, and you have to do all of that work. And even still, if you've ever looked at competitive programming code, some of it can be really efficient, but really bad and really hard to read. So algorithmic complexity is great for efficiency-based optimizations, but not always great for just code readability. So now we can think differently. Immediate function complexity is an idea that we should assess the immediate share of labor performed by the function before it passes control to the other subroutine. And we can assess it in a way that will yield some interesting conclusions about the way we should refactor our functions, even though it doesn't have any impact on the efficiency. Right. So let me show you how we do this. Let's say we have this very simple function, some function f. It has, takes address, queries an endpoint, assesses the error. The indentation is broken. It's fine. And so it either passes a filtered and sorted response here or the error itself. Now, this is the way we can rewrite this function. And again, the indentation is broken, but it's fine. This is the way we rewrite this function, and we separate two components that I call state space and state transformer. I don't suggest you use that in your actual code. This is just a model for thinking about it and to demonstrate the idea of the immediate functional complexity. So first of all, state space. To extract the state space of a function, you simply take its parameters, return values, and all of the variables that it declares within the body immediately, right inside, and you put them in a separate structure. And by analyzing some properties of this structure S, we're going to derive some interesting conclusions later on. Now, logic is a function that operates on the state S, and it changes it and gives you another state S. These two functions are there for clarity. So for example, the feed takes argument, returns S, and result takes S and returns the return values from the function. So all these four things are in a way equivalent to the previous one. Now let's talk about the first one, which is state space. Right. My friend made me do that. So to assess the state space of the S structure, right, and this can be formed for any function you're reviewing, we need to review some basic type theory just for, maybe some people don't know. It's fine. So there's some types which are an enumeration of distinct values, right? Like let's say int32 type just enumerates a bunch of integers. It's like a set, literally, in discrete mathematics. Month, let's say if this is an enumeration that we define ourselves, month has 12 items within it, so it's a set with size 12, right? So that's easy. Now we have product types. So product types contain other types in them, and to calculate the number of elements that each product type has, you simply multiply each field of it, the size of that field by the size of this field. So let's say if there's about 2 billion integers in here, and there's 12 months here, the total number of possible elements of this tuple type is 2 billion multiplied by 12, roughly. So this is the size of the set of values that belong to this type. Same can be done here. You multiply the number of int32 by number of all possible strings. And here, this is like a special case. This would be 2 billion, the number of integers, to the power of 42. So you just multiply 42 times the same number. This is how you calculate the number of elements in a product type, right? And now that we reviewed that, my suggestion is that going back to the state space struct S of a function, we should seek to make it smaller. So we should minimize state space of a function by using different techniques I'm going to review later. First of all, why? Representational accuracy is one. So if we choose, and this is a common thing, to represent 1 month as an integer, what we're going to find is that the representational accuracy of that type is going to be very small. What do I mean by that, right? There's 12 months, aka 12 valid expected states of that integer from 1 to 12, and there's 2 billion integers in the int32 type, which means that if you represent a month using an integer, you're going to have this representational accuracy. This is 0.0000006%, right? That's no good, which is why you use enumerations. And same can be argued for a function. If your functional state space is huge, that means you are allowing yourself to develop code within a space where most of the values and states within that function's flow are invalid or undesirable. Okay. One trick that we can use is discriminating on the tuple, where this is like a common pattern in Go. I think all of you recognize it. We have one value that is the OK value, like let's say the posts and the response, and the error value, right? What is this type? Is this a sum type or a product type? Anyone? Product type, exactly. So the state space of this type is the multiplication of the number of possible values of t by the number of possible errors, correct? Now that's a lot. But if we conventionally say that our functions are going to either return the t or an error, never both, we basically make it, conventionally, a sum type. So the number of possible states becomes the number of t plus the number of errors rather than the multiplication of them. And then representational accuracy rises. Other languages have this kind of typing mechanism called discriminated union type, which Go doesn't have as of yet, but you can search it in your free time. Another way to decrease and make state space smaller is by breaking functions down, right? So if you decouple parts of a function into smaller functions, then they will have mathematically a smaller state space because they will have fewer variables, they will accept fewer parameters, and also, the return type is probably going to be smaller. So by having this big, angry, bad, hard to read function f, you decouple it into query, filter, sort, whatever the parts are, they will most likely be smaller, and you will see that in the state space of those functions separately. Last trick, pipeline it, right? A function that has one return statement, it is one line, and it's just a bunch of functions. You take the parameter, pass it to one function, to the other, to the third, return the value. Has no variables within it, therefore the state space is by definition limited to the parameters and the return types, which is smaller than having intermediate variables, so that eliminates it, and that's what you should do. Also very easy to read if you give those functions proper names. Now a bit religious. The 11th less known commandment God gave us is love thy teammate, but it was written in binary and no one got it back in the day. What do I mean by this? Nowadays, there is research into cognitive load and how many things people can hold in their heads. People prefer 6-second TikTok videos to, let's say, 10-minute YouTube videos. Why do you think that those same people are going to be able to hold 20 variables you put into your function in their heads while they read it, right? That's unreasonable. They're going to probably forget it halfway through. You will get bad PR reviews that are very, very like surface level. They're not catching any bugs. Don't do that. Write smaller functions. Love thy teammate. Now talking about state transformers. What is a state transformer? So given some state space S of a function, as defined before, a state transformer can be defined as type T that just takes a state space and returns one. For example, the trivial ones. Identity or knob operation, right? That doesn't exist in Go, but basically it takes a state space, returns the same one. Or an assignment on the state space, right? Just changes one field into the other. It's very obvious that those are composable. And there are some branching transformers. So for example, if can be represented as a function that takes a Boolean and two branches, two different state transformers, and choosing based on the Boolean chooses one or the other. Switch can be represented in a very, very similar way, except we take a map of, comparable to transformer and the default transformer. And this is pretty much how you can describe everything within the lingo of state transformers and state space. This is the mathematical framework I was talking about. And using this, you can use this branching combination rule, which is like you just make a diagram and you kind of count, okay, if this has 3 branches and this has 1 branch that doesn't have any more branching, then in total this is a branching factor of 4. So you calculate this branching factor and you can access it too. And again, by the way, loops add 1 to the branching factor because they can all be represented as 1 if due to Church-Turing conjecture. Read in your own time. So yeah, by assessing the branching factor, you should again make it smaller. You decouple functions, you break them down, and you receive a lot of benefits. What are those benefits? So first of all, function is a basic testable unit of code. So if you make its branching factor smaller, which is an estimation of the number of possible edge cases, right? If you make its branching factor smaller, your testing is easier. You don't have to write as many test cases for it. In fact, if your function has 1 branching factor, then it's 1 test case. Very simple. So breaking it down into smaller functions will reduce their immediate branching factor. Bulkier functions with a lot of logic in them also require longer, more involved test cases, in particular setup and teardown, which is harder to maintain, read, and whatever else, right? And in most cases, branch extraction, the technique that I was mentioning before, also splits the state space. So by attempting to reduce the branching factor, you usually also reduce the state space of those smaller functions that you get out of it. Now, this is pretty much it for the talk, and now to connecting the dots. The neat thing about immediate functional complexity, as I hope I have demonstrated, is that by assessing the state space and the branching factor of a function, you can get these very measurable and quantifiable metrics by which you can judge the quality of your code. And you can use them to derive principles like dry and solid decoupling, composition. You can derive them and use them, right? But you derive them from objective measurable things instead of your opinions or feelings. It's clearly defined, quantifiable, and apparent. And this is good. It's a simple mathematical model that leads to a lot of great advice. And now to the questions. Do we have time for questions?
Oh, yeah, we have so much.
Really a simple question. So you advise to reduce the number of branches. So basically, GoCycle is one of the tools you can use to check how complex is your code by each of the functions. Are you using it already as part of your CI/CD?
Wait, could you repeat what function?
GoCycle is a tool in Golang which check GoCycle.
I'm not aware.
Check the cyclomatic complexity, which is the number of branches you were discussing. So if you're not aware, good. You should start using it then.
All right, I mean, that's good. So there is apparently a tool to assess your branching factor.
Yeah.
That's perfect, yeah.
Yeah, it's a great thing.
So now we're bringing automation into the theoretical model. That's great.
Any other questions? I can't. No?
If there was anything that is unclear, like maybe you don't have a question because I didn't explain it something good enough.
I have something to say.
This guy is going to save you for questions.
All right, are you ready?
Yes.
That presentation was awesome in content and delivery. Fantastic.
Thank you so much.
I felt you were feeling that you'd messed it up in some way. I loved it. That's what I wanted to say.
Not a question, dude.
I'll do a question then.
Thank you.
How did you get so good at such a young age?
I had a stage fright and I joined the debating society when I was 16.
Oh, okay. It's working, man.
Does anyone else want to compliment this man? But yeah, thank you very much for your talk. One final round of applause.